So the universe is composed of matter and energy. We've talked a lot about matter, and we need to talk about energy. In chemistry, we study matter, but energy affects matter, so we also have to learn about matter. So here we got some words that we use in everyday life, but in science we use them slightly differently. So we think energy, right? Think energy drink, I need more energy. What exactly is energy? Science defines energy as anything that has the capacity to do work. Okay, well then what's work? Work is not, something you don't like doing that people give you money for. Work is a force acting over a distance. So energy is the capacity to do work, and work is equal to a force times a distance. So here's the stapler on the bench, and if I push it across the bench, I have exerted a force through a distance. I just did work. Didn't specifically get paid to do that, but that was work, right? And then heat. Heat is the flow of energy. It's energy moving from one thing to another, and that flow is caused by a difference in temperature. So we can get energy being exchanged between objects through contact, as like with a collision. So we have to keep energy, heat, and work straight in our minds. So energy is a quantity. Something can have energy, it can possess energy. Heat and work are ways of exchanging energy with other objects. So energy can move into objects or out of objects. Heat and work are the process by which energy is transferred. There are different kinds of energy. Kinetic energy is the energy of motion. When something is in motion, it has energy. Thermal energy is a type of kinetic energy. It does have to do with motion. It's associated with temperature. What happens when you heat up a gas? What do the particles do? They move faster, right? You heat them up. You're providing them with energy. They're moving faster. Their kinetic energy is greater. Their temperature is higher. We're going to use billiard balls as an example here. So here you have the cue ball rolling towards this purple ball. The cue ball has energy due to motion. It has kinetic energy. The purple ball is just sitting there. When the cue ball hits the purple ball, there is a transfer of energy from the white ball to the purple ball. And that is work. And so the white ball, the cue ball, transfers its energy to the purple ball, and now the purple ball moves on. So work has been done. The other broad category of energy is potential energy. And this is energy stored in an object or energy associated with the composition and or position of the object. I usually have a marker. Where's my marker? Well, we'll use a red pen. So if I hold this red pen out, it has potential energy because it's elevated above the floor. Right? And what happens when I let go of it?
Gravity. It falls.
Gravity, and it falls every single time. When it's down on the floor, it has less potential energy because it's lower. Chemical energy is a form of potential energy, but instead of being a position above the ground, it has to do with relative positions of electrons and nuclei in the atoms and molecules. So it is a stored energy, but it's due to the composition and still due to position, but on a very, very small scale. So you drop a ball, gravitational potential energy causes it to fall. What happens to that potential energy? Does it just disappear? No, it's transferred or transformed into kinetic energy. Because when you hold the ball or the red pen out, it's not moving very much. When you drop it, now as it falls, it gets faster and faster, and so it's got more and more kinetic energy and less potential energy. So energy is the capacity to do work. There's kinetic energy due to motion. Thermal energy is a part of or a type of kinetic energy. That's the energy associated with temperature. Pointer's broken again. It's awesome. There it is. Potential energy due to position or composition. One that we're very interested in chemistry is the chemical energy, a type of potential energy associated with positions of the particles inside matter. So those are broad categories. Here are some others. Not really going to quiz you on these, but just to go over them. Electrical energy. This is a kinetic energy, and it's associated with the flow of electrical charge. Electric current is the flow of electrons. Electrons are moving when the current moves, so electrical energy is kinetic energy. Heat or thermal energy, we've talked about that. Kinetic energy associated with molecular motion. The sun gives us energy on our planet, right? That's light energy or radiant energy. And this is also kinetic energy, and that's associated with energy transitions in an atom. Nuclear energy is a form of potential energy, and that's coming from the nucleus of the atom. We'll talk about that later as well. And chemical energy, potential energy due to the structure of the atoms, the attachment between the atoms' relative positions to each other, all of that kind of stuff. So matter is conserved, law of conservation of mass or matter. Energy is also conserved. So energy cannot be created, energy cannot be destroyed. But it can be converted from one form to another. Just like with the dropping of the pen had high potential energy, and when I dropped it, the potential energy was converted to kinetic energy as it fell. Here we have an example of a woman pushing down on a ball on top of a spring. You push down, she's applying mechanical potential energy, and then when she releases the ball, the spring expands and the ball has kinetic energy and shoots up in the air. There's a conversion of energy from one form to another. The total energy at the beginning is equal to the total energy at the end. Okay, just like with the matter. We have to define what part of the universe that we're looking at, especially when we talk about energy. So we talk about the system and the surroundings. The system is whatever we're studying energy changes inside of. And so you can define a system however you want. We've got the Meeker burners going here because it's cold in the classroom. And so there's a combustion reaction going on there. And so we could define the system as the gas burning in the flame, or we could define the system as the whole room. We can define it differently. The surroundings are everything outside the system, the entire universe. And that's what the system can exchange energy with. So we look at the exchange of energy between the system and the surroundings. So if energy is conserved, that means the amount of energy gained or lost by the system has to be equal to the energy lost or gained by the surroundings. There's no energy bank where you can just go and get extra energy. So here's an example, looking at the system, pretending it has an energy gauge, and we're saying, well, it's half full. The surroundings also having an energy gauge, and we're saying, well, that one's about a quarter full. So if there's energy transfer from the system to the surroundings, then after the energy transfer, the system has lost energy, the surroundings have gained energy, and the amount of energy is the same If we take the sum of these two and the sum afterwards, they're the same. If we look at how much this lost and how much this gained, it's the same amount of energy. Well, energy is a quantity and it can be measured, so we need some units. Kinetic energy is directly proportional to the mass and the velocity of an object. So the SI unit of energy is the joule. The symbol is a capital J. This is a relatively small unit, and so in chemistry we often end up using kilojoules. Kilo means 1,000, so 1 kilojoule is 1,000 joules. And just sort of for reference, here's a light bulb. That would use 0.10 kilowatt hours. That's the unit that the power company uses. That would be equivalent to 3.6 times 10 to the 5th joules in an hour. So the joule's a very small unit. Joule is a derived unit. It's not one of the base units. The joule is a Newton times a meter. We kind of got into this on Monday when we were looking at that root mean square velocity problem. Energy is a force exerted through a distance, right? So it's a Newton, which is a force, times meter, which is a distance. It's also equivalent to a kilogram meter squared per second squared, because Newton is a kilogram meter per second squared. So if you're one of those people that cares about units and how they cancel out, that's information you'll be interested in. If you don't care so much, I'm not going to test you on that. A calorie is also a unit of energy. Calorie with a lowercase c is defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So that is a meaningful unit in terms of chemistry. A calorie can be related to joules. A calorie is 4.184 joules, and that's an exact conversion. Now, the calories that you may have counted if you ever went on a diet are nutritional calories. And very confusingly, those are calories with a capital C, and those are actually kilocalories. So a nutritional calorie is actually a kilocalorie or 1,000 calories. So I will not intentionally trick you, but I have inadvertently tricked students on exams before. Capital C and lowercase c on the calorie are significant, and they are not typos. Okay, so if it's a capital C, it's a capital C. Here are some energy conversion factors. We're not going to use kilowatt hours much. Power company uses it, so it's just kind of there for reference. We're going to use calories and joules for the most part. And just for interest, energy use in various units. Amount used by a human body in running 1 mile. So in nutritional calories, 100 calories. That's one of the reasons I don't run, because it just doesn't seem worth it. 100 calories, not worth it. For an hour? No, a mile. For a mile. So a kilowatt hour, that would be 0.12. In terms of scientific calories, that's 1 times 10 to the 5th, because that's 100 kilocalories, or 4.2 times 10 to the 5th joules. We have different units for energy because they are useful in different situations. Any questions?